we can start. This morning we will hear about fluid mechanics, which is an important subject, I think, but we exploited the occasion of this conference for presenting to Professor Seminara a well-deserved medal which we give, I mean M&MoCS Center, to scientists who contributed to engineering sciences. Okay, so this is the parchment. Ivan is shooting the picture. And this is the Beltrami medal. You know, Beltrami was in the as I told you, yes, for having equations for equilibrium of solids, which are the basis of modern civil engineering. So I think that we have chosen, of course, an Italian for this prize, because albeit in Italy we try to do what we can for underestimating our country, we should try to fight and try to remember to French, above all, that we are doing a lot. Okay. Let me pull the leg off. Okay. So, Professor Seminara has done a lot. He will tell us, I think, about his whole career. We gave him the prize before because he has nothing to demonstrate. Okay, so this is a lecture not for getting the prize, but it is a lecture after the prize.
Thank you.
Okay.
Thank you, Francesco.
So please, I give you
the word. Of course, I should start thanking Francesco. I was talking to Mario yesterday, and I said that I had never understood prizes, to be honest, because we scientists have a privilege. We do work because it's fun for us. We have already this privilege, so having also a prize is too much. Anyway, of course, I thank you, and I was not sure to deserve any prize, so I looked at the M&MoCS, and I understood that the Beltrami Prize winners are expected to have transversal capacity to reach multidisciplinary fields. So I decided to give you a short account of some of the work that I did to see how I personally interpreted this idea of multidisciplinarity. I had many companions. Oh, sorry, I have to learn how to, of this adventure. The first group are all my former students, now professors in Italian or foreign university. This is a group of foreign colleagues that I had the pleasure to interact with. And Enrico Marchi was my mentor. He was professor of hydraulics in Genova, and he was also a member of the Accademia dei Lincei, because, yes, I was educated as a hydraulic engineer. And when I got a degree in hydraulic engineering, that was a professionally oriented discipline. Still now, it is a professionally oriented discipline. So research was nearly only experimental. Because at that time, we are talking about the 70s of the last year, very little was known about turbulence, and most fluid flows of relevance to hydraulics are turbulent. But I was inclined towards theoretical fluid mechanics. I wanted to study theoretical fluid mechanics, so I discovered that a beautiful subject to do theoretical fluid mechanics was biofluid dynamics, for one simple reason, that it is all the flows in the circulatory systems are mainly either laminar or at most transitional. So it was the heaven for theoretical fluid mechanicists at that time. So I decided to move to Imperial College, which was, it was mentioned last night for other reasons, but it was an important, I would say, one of the most important places where to do this kind of work, because there was a professor in physiology called Colin Caro, who was able to establish a small physiological flow studies unit where you would find physiologists, cardiologists, clinicians, engineers, chemical engineers, all sorts of engineers interacted an environment, a beautiful environment that in Italy it would be impossible to find nowadays, okay? So Colin Caro was interested at that time in the origin of atheroma, the fatty streaks, which are associated with atherosclerosis. And the theory at that time, the prevailing theory, associated atheroma with the presence of acute elevated shear rate. So the shear stress, which is the action of the fluid, tangential action on the arterial walls, Fry thought should be very high in order to produce atheroma. But in 1971, Colin Caro changed completely the paradigm. He essentially stated the opposite. And he stated that fatty streaking and early atheroma arise in those regions in which arterial wall is expected to be relatively low, exactly the opposite. And the rationale behind this change in paradigm was that the low shear stress implies thicker diffusional boundary layer, and so a more difficulty for lipoproteins to diffuse into the blood. So these were two completely opposite theories, and so the questions that arose were two questions. In which arterial sites are fatty streaks preferentially observed, and are they associated with high or low shear stresses? Okay, so this is what you observe. This is a paper, 2004 paper, so more recent, but it is very clear that fatty streaks concentrate either in bifurcations or in the aortic arch, you see, but only in the inner aortic arch, not in the outer. And so the question was, why? Why only the inner and not the outer? Now, flow in the aortic arch, it has a Reynolds number around 10 to the 4. And curvilinear streamlines. So the first question that came to my mind is, can it be centrifugally unstable? I don't know how many of you know, most certainly know, that if you have a flow between the two rotating cylinders, or just one of them rotating, okay, viscous incompressible flow, it is very well known since the beginning of the last century, a famous work of Taylor, that this flow is centrifugally unstable in the sense that above some value of the Taylor number, which is the product of a Reynolds square, the square of the Reynolds number, times some curvature ratio, and which measures the ratio between destabilizing and stabilizing forces, destabilizing centrifugal and stabilizing viscous flow forces. The basic state, which is purely unidirectional flow, becomes unstable, and you observe these counter-rotating axial symmetric vortices. But of course, the flow in the aortic arch is much more complicated. First of all, it is pulsating, and also it is three-dimensional, and curvature-driven secondary flows are generated. But at that time, we are talking about 50 years after Taylor's work, no one knew about whether Taylor instability would occur also for unsteady flows. So the first step was obviously to study the centrifugal instability of unsteady flows, which means essentially having a cylinder which oscillates harmonically in in a fluid. And also, for those of you who know some fluid mechanics, if you increase the frequency of the oscillation, the viscous effects concentrate in very thin boundary layers, thinner and thinner as the frequency increases, because the characteristic thinness of the viscous boundary layer, which is called Stokes layer, is the square root of the kinematic viscosity divided by angular frequency. In the case of the aortic arch, this value delta is around 0.5 millimeters, which is much smaller than the radius of the aortic arch. So I ended up deciding to study the prototype of the oscillatory boundary layers, which is a Stokes layer. In other words, the layer of flow of viscous incompressible flow, which is generated by the pure oscillation of a cylinder in an infinite fluid. And this is the basic state. The spatial scale now is no longer the gap between two cylinders, but it is the thickness of the viscous boundary layer. And so the Taylor number now takes this form. But at that time, as I say, no one knew if you would get Taylor vortices also in an unsteady flow. So the first thing that I did was to perform an experiment, a very simple experiment. I would call it a Taylor type experiment, where I visualized the flow generated by a circular cylinder oscillating in this larger cylinder. And actually what you observe is when the Taylor number exceeds a critical value of about 150, you get the formation of these Taylor vortices counter-rotating with a wave number, a dimensionless wave number 0.88, which means that the wavelength of these vortices is roughly 7 times the thickness of the boundary layer. And you also observe a secondary bifurcation later in the development of the vortices. Okay, so I tackled this problem theoretically, doing a classical, not very classical in this case actually, but anyway, a linear stability theory, assuming, of course, axial symmetry, taking advantage of the periodicity of the basic state when using a Mathieu-Hill type of expansion. I don't know how much I should go into details, but anyway, you end up with an infinite system of ordinary differential equations that in this case can be solved with a suitable expansion taking advantage of the exponential decay of the basic state. Anyway, you end up with an eigenrelation which relates the complex omega with Taylor number when number. And this is what you get. You get a marginal stability in the plane Taylor number wave number, a marginal stability curve, a minimum, and the minimum corresponds to 7.3 thickness of the boundary layer in terms of length of these vortices, and the critical Taylor number, which was 150 roughly experimentally, is 164.4, so a fairly good agreement. Also, the perturbations are shown to be synchronous with the basic state. I then did some more analysis to understand what happens in the weakly nonlinear regime, but I will be very quickly. I don't want to bother you with too many details. And anyway, you just make an expansion in a neighborhood of condition, classical expansion, introduce a slow time variable, use multiple scale technique, and with some algebra, you end up with a Landau-Stewart amplitude equation, which describes how the amplitude of these vortices evolve in time, okay? And you can show that this coefficient A2, the sign of this coefficient, for those of you who know the amplitude equation of Landau-Stewart, controls whether the bifurcation is subcritical or supercritical. In this case, it is subcritical. Okay, this is enough for this part. Let me just say that that was only the beginning of a lot of work, not by myself, but a lot of other people worked, of course, on the origin of atheroma. But all these works confirmed that atheroma arises where low or highly oscillatory wall shear stresses are concentrated.
So both were right.
Sorry?
Both were right.
No, because the high frequency, the fact that the shear stress is oscillating doesn't mean that it is high. It just means that it is oscillating. The main reason, essentially, the low shear stress implies that the blood has more time to diffuse. And the same when you have an oscillating boundary layer, because it changes the direction.
So low and high here refers
Either low or high. No,
frequency.
it's low or highly oscillatory.
So it is
Walls.
with frequency.
Okay, the frequency, that's right. But nowadays people do not do much theoretical work, but let's say computational fluid dynamics has become the new heaven for this field. And you can check this if you have a look at this book, which has also some professor from L'Aquila. He discovered me among the authors. And there is a chapter on numerical modeling, and there are 10 pages of references, just to give you an idea of how many people work on this topic. Okay, enough for the first part of my career. When I went back to Genova, I continued to work, of course, on the basic fluid mechanics, but not so much on biofluid dynamics, because the environment, I must say, was not as exciting as at Imperial College from this point of view. And I got very much interested in a second area, which is let's say, the understanding the variety of natural phenomena that you observe when fluid flows along an erodible boundary. Okay, which means everything, means water and sediments, but it may mean also, of course, wind and sediments. There is a really astonishing variety of natural patterns which are observed. That can be, let's say, organized using different paradigms. The first paradigm can be the spatial and temporal scales. So you get scales of the order of 10 centimeters. These are fluvial ripples. These are coastal ripples. Then you increase to 10, 100 meters. These are fluvial dunes in the Paraná River. You see the wavelength of the order of 100 meters. And this is the equivalent in the coast. This is the Belgian coast. And these are called sand waves. Then you can also increase again the spatial scale, and you get bars. Bars are, I will talk about bars in a moment, because they are the fundamental unit of all rivers. So understanding bars means understanding the morphological evolution of rivers. They can be organized in single rows, like in the Rhine River. These are called alternate bars, or in multiple rows. In this case, the river is called braided river. Even larger are, of course, deltas, estuaries, and these strange sandbanks, which are huge, huge bed forms, which hinder navigation, so are very important, and they are observed along the Dutch coast. You can also have organize these patterns according to a second paradigm, erosional versus depositional. Of course, comparing the amount of sediments that the stream is able to carry with the amount of sediments that are supplied to the stream. So if you supply less sediment than the stream is able to carry, then you get, these are the so-called bedlands. They are observed in California, and these are obviously erosional environments. In a case of alluvial fan, you get more sediments from the incision, which is very steep, than the alluvial fan is able to carry, and so you get a depositional environment. Third paradigm, bed forms versus plain forms. The perturbations may affect only the bottom, or may affect the plain form of the pattern that you are observing. The typical case is meandering rivers. I'll give you some examples. This is the river from which the name meander arises. This is in Turkey. It's called Büyük Menderes. It debouches into the Aegean Sea. These are meanders observed in Venice Lagoon. They dissect the wetlands. This is one of the most spectacular set of meandering that you can observe. This is in Utah, and they are incised into bedrocks. This is a meandering turbidity current. So we are in the delta of the Congo River. This is a submerged meandering stream. And finally, meanders have been observed on the Martian surface, of course. Not of course, because actually it has been a great discovery. So the fourth paradigm you can use is distinguishing between free and forced patterns. Free are spontaneous, arise from instability. Force means that there must be some external forcing condition which determine their formation. Okay, now the question is, why do we study this? Just because it is an intellectual challenge? Of course, yes. Of course, I am interested in understanding, first of all. But having said that, there are other reasons. Of course, the natural evolution of sedimentary environments may threaten, as we know, the life of human communities. I just want to show you what you can do today with Google. This is what you observe in the Rio Ucayali, which is a tributary of the Amazon. And look, in 10 days, in 10 years, assuming it works. I don't know why it does not work. Okay. Each step is 1 year. So you see how quickly this river evolves and, of course, threatens the city of Pucallpa. So understanding these processes has obvious implications. This is the Rio Ucayali, along with the Rio Maranon. They are tributaries of the main Amazon River. But I want to... The second reason is that something that has not been done in the past, not enough. Predicting the impact of engineering works on natural evolution is a fundamental step of designing. In the past, this was not done because we were not aware of the consequences of ignoring the impact. Let me give you some examples. One example: Mississippi River Delta. Okay, the Mississippi River has a huge delta which debouches into Gulf of Mexico, right? Now, in order to allow navigation through the delta, which is fundamental for the United States in passing, of course, okay, they have constructed levees along the Mississippi in the delta. So the consequence of doing this is that you hinder flooding. The Mississippi does no longer flood into the coastal wetlands. And if it does not flood, it does not deposit sediments. Now, you may know that the equilibrium of wetlands is a very delicate equilibrium between the amount of sediments that the river deposits during floods and the sea level rise and subsidence, which are also natural processes. If you remove the deposition, you end up with what has happened in the Mississippi River. It has lengthened so much that now it discharges sediments so close to the edge of the continental shelf that all the sediments go into the incision of the continental shelf and are discharged in the abyssal plains where they do never come from. They do not return. And so this means that there are no longer sediments for replenishing the coast, and the whole coast of Louisiana is being eroded. So understanding all these complex phenomena is important also for engineering. Now, having said that, these patterns are ubiquitous. They are relevant for engineering. Geomorphologists have done a lot of work to describe these processes, but nothing has done from the mechanical point of view until the 70s of the last century. So let me say a few words about the problem of morphodynamics from the mathematical point of view. It is a free boundary problem. It is a free boundary problem for two reasons. Because we have a free surface, like in any open channel flow or any, but we have a second free surface, which is the erodible interface, which is also free in the sense that it is eroded, so it evolves in time. Okay. Now, if you denote by Cm the packing sediment concentration, by eta the bed elevation, by QS, the local depth integrated sediment flux per unit width, you can just write an equation which is a mass conservation equation, which has this form. And if you want to study processes on a much longer time scale, say geologic time scale, then you have to add also the effect of tectonic uplift and subsidence rate. This problem is obviously coupled to the hydrodynamic problem, because in order to do anything, you have to evaluate QS. And this is a huge subject. You have to solve the problem of sediment motion under the action of hydrodynamic forces. So a lecture would not be enough just to outline how you can do these things. But of course, we have to go back to the argument of Mario Pulvirenti yesterday, the problem of scales. You can study sediment motion in great detail, okay? Nowadays it is much more possible because you have useful computational tools, but you cannot study detailed motion or sediment motion coupled with the understanding of large-scale processes of the kind that we have. So we have, in some sense, parameterized sediment motion and use computational fluid mechanics to check how good are our parameterization. Okay, this has been done for several decades. Essentially, we can say that the dimensional sediment flux per unit width is a function of, incidentally, the way QS has been made dimensionless was proposed by Einstein, which is not Albert Einstein, but his son. Hans Albert Einstein studied sediment transport. But the story says that he went to talk to his father, asking what subjects were very important. And he said, according to the story, that there were two main subjects, quantum relativity and turbulence and sediment transport. But look, turbulent sediment transport are very difficult. This is the story. Okay, so QS is a function of the dimensionless bottom stress, shear stress, which is called Schill's number because Schill's was the first to study this, a particle Reynolds number, which is a dimensionless measure of the size of sediments, and the local bed slope.
This equation is phenomenological or maybe...
This is based, there is a lot of analysis, theoretical analysis with simple models, okay, which corroborate the experimental observations. Originally it was only experimental, but nowadays has been, but of course the only answer, okay, I don't have time, so I don't want to, but the computational work that is being done nowadays is very useful to see to what extent these work. And they have found that they work. They work in an average sense, not locally. Okay, so there are discrepancies locally, but not in an average sense. Okay, of course, if you want to calculate the bottom shear stress, you need to solve the hydrodynamic problem. And of course, here you can use different ways of describing the hydrodynamics depending on the scale, again, of the process. You can use full Navier-Stokes equations or average forms of these equations. Okay, solving this problem, what does it mean? It means 3 steps. First, equilibrium. Second, is provided the equilibrium exists, is it stable? And third, provided it is unstable as it is, how does the process evolves? Now, let me show you the simplest case that one can imagine. So we have a straight rectangular channel, steady flow, erodible bed, homogeneous, constant width, and inerodible banks. For the moment, the banks are inerodible. Then the mass conservation implies that eta cannot change in time. The QS is constant, so the stress is constant, and so you end up with uniformity. So a uniform flow on an open channel can be in equilibrium provided the flow discharge, the sediment flux supplied are constant, and there is an equilibrium channel slope and a uniform flow depth. This is very simple. Now, first question, is this equilibrium unstable? Of course, you have seen how many patterns you can generate, but let me describe the fact that it is unstable in the simplest way I can. But this doesn't work anymore. Why? This doesn't work. Non funziona. Forse è la batteria che scarica? Vado avanti. No, non funziona neanche il computer. Chiudo e rientro? No, è il computer evidentemente. Adesso vediamo se funziona. Sì, funziona. Ok. As I say, destabilizing mechanism. I will describe it in 1D, which is simpler. So let us perturb the bed elevation with a small amplitude perturbation, wave number lambda, complex frequency omega. If we perturb the bed elevation, we will have a perturbation, of course, in sediment flux, but not necessarily, in general, not in phase with the bed elevation. So if you substitute from these two quantities in the sediment continuity, you just simply show that the complex growth rate depends on this phase leg. And the phase leg depends on the flow characteristics, of course, grain size and wave number. So there must be a phase lag between sediment flux and bed elevation. I will now describe in more detail the formation of fluvial bars because they are extremely important in the whole subject. As I said before, they may occur in alternate bars, so in single rows. They may also occur in multiple rows. In this case, they are called braided rivers. You observe these also in the laboratory. These are our experiment in the laboratory, and the characteristics of these bar are periodic sequences of deposition and erosion areas, riffles and pools. They have oblique fronts. They are wavelength scales with channel width, and they migrate downstream. You can do a very straightforward theory to understand these using a shallow water model, which is the simplest and adequate model to describe the hydrodynamics. Perform a classical normal mode analysis. This number m describes how many rows you will have. So m equal 1 is the alternate bar mode. M larger than 1 is the multiple row bar mode. If you do the classical analysis, you end up with an eigenrelation which relates the complex frequency with the wave number, of course. But look, the important parameter here is beta, which is the aspect ratio, the ratio between the width and the depth of the channel. This is the important parameter which plays a role in this case. Tau star is the shield stress, and this is relative bottom roughness. You get a classical marginal stability curve, and you are able to define a formation criterion. So the alternate bar mode occurs when beta is larger than beta C. So the channel must be wide enough in order to have bars. Okay? If it is too narrow, you don't observe bars. Okay? This is the main discovery. Also, this is an important point. The most unstable modes are migrating, but also stationary bars are allowed, non-migrating, but they are not the most unstable. So they are not observed unless some mechanism that I will show you later is important. Comparison with observations, relatively good, I would say very good, because the only area where it does not work very well, the theory, is close to the critical condition for sediment motion. So, which means that you are perturbing a state where sediment motion does not occur everywhere. So the theory cannot work perfectly. We did a lot of other work, but I don't know whether this is the right place to discuss it in detail. Let me just say that for those of you who know about instability, instabilities of convective type. Instabilities are divided into two classes, convective and absolute, according to some work that was done originally in plasma physics and then extended to hydrodynamics by Huer and Monkewitz. We proved that analytically that the bar instability is of convective type, and numerically, strongly numerical simulation show this, because as you see, you generate a sequence, a group of waves starting from an initial small randomly distributed perturbation, then these wave groups migrate downstream, and they leave the upstream domain unperturbed. This is the sign. This is what tells you that it is convective. It means that you have to force the perturbation continuously if you want to see it. If the instability were absolute, you would not need that, okay? This also confirms also the weakly nonlinear analysis, which shows that in this case the amplitude equation is of Ginzburg-Landau type, and so it describes this evolution of wave groups in the weakly nonlinear regime. And this is the what you observe, what you get numerically. It reproduces the formation of oblique fronts. Okay, enough for bars. Now let's go to meandering. Alternate bars generate a meandering pattern within a straight channel. Okay, the channel banks are straight, but the Talweg, which is the locus of high speed, is meandering, as you can see in this experiment. So geomorphologists were convinced that alternate bars were precursors of meanders. And this has been, they have thought that for a long time, also after we did some work that I will show you. But now they are convinced that they were wrong. Let me show you why. We did this work in a series of papers on JFM. So now let's understand, how do meanders evolve? They evolve because the outer banks are eroded and the inner banks undergo deposition. So the channel shifts, okay? Bank erosion is a complex process. It has two components because there is a continuous contribution due to grain removal. The water removes grains continuously. But also, the most important part is the intermittent contribution due to bank collapse. Banks collapse mainly after floods. But anyway, you can try and describe this for a single event, but you cannot use a single event description to describe processes which occur in 100 years. So what you have to do is to try and define an average bank erosion rate. In other words, to describe as a continuous process something which is intermittent. Anyway, now let's consider the axis of the channel. And let's denote by theta the angle that the tangent to the channel axis formed with some Cartesian coordinate. Now theta is a function of s, intrinsic coordinate, and time. But s is itself a function of its original initial value and time. So if you do some kinematics and define by zeta the rate of displacement or lateral migration, you can show that theta satisfies an integral differential equation. So an equation which has both derivatives and integrals, for those who are not familiar. And this is a very important feature because why is it integral differential? For a simple reason, that this equation must describe the history of the deformation process. And the history, the lengthening of the channel, is inside this integral. It is nonlinear for two reasons. It is nonlinear because of this term here, geometric, but it is also nonlinear if you describe the hydrodynamic process taking account of nonlinearities. So it's a complicated form, but as usual, let me use this to explain meander instability in a very simple way. Consider a straight channel, okay? Basic state. Then perturb, again, small perturbation, small amplitude, lambda, meander wave number now, omega, complex frequency. And now assume, we don't know exactly how bank erosion works, but assume for the moment that bank erosion is proportional to curvature and in phase with curvature, which means that the maximum erosion occurs in the peak of the meander. Okay? If you substitute in integral differential equation, you end up with a dispersion relationship which tells you two things. First of all, that the imaginary part of omega, which is the growth rate, is proportional to lambda square, which means that the shorter the meander, the higher is the growth rate. So it is unstable, but there is no peak, there is no preferred wave number. But the second is even worse, meanders do not migrate. And we know that meanders do migrate. So let us slightly complicate the problem by simply assuming that the erosion rate has a phase lag relative to the curvature, delta. And then if you now substitute into the nonlinear integral differential equation, you find exactly what happens. Meander growth rate has a peak. There is a preferred wave number. Meander speed is positive if meanders migrate downstream, so it is positive if the erosion peaks downstream of the band apex, and it migrates upstream if the erosion peaks upstream of the band apex. Now, the phase lag between flow perturbations, hence bank erosion and curvature, is a crucial ingredient of meander growth. So you now have to solve the problem, the hydrodynamic problem, and you must first have some relationship between the hydrodynamics and the bank erosion. The simplest that you can envisage, but it works according to some field observations, is that the erosion rate is proportional to Stram coefficient to the difference between outer band velocity and inner band velocities. It has various advantages that I cannot describe in detail. If you do this, you get the growth rate as a function of meander wave number. You get something which is reasonable, which is that the preferred meander wave number is in the range of 30 to 10 channel width, which is close to what is observed. And but also you observe something, that when we did this work, Paolo Blondeau and myself, when we did it, we did not understand it immediately, because we found a resonance effect. So for some value of the aspect ratio and an associated value of the wave number, the peak and the response is infinity. Let's say is unbounded. How is it possible? Well, it looks like the linear meanders behave like linear oscillators, which resonate in some conditions. Why? Let's go back to the bar problem that I described before. If you remember, I stressed the fact that there are also stationary solutions of the bar problem. In other words, the system admits natural bars, a natural solution, which is a free bar which does not migrate. So what happens is that curvature forces that natural solution if you are exactly in the range, that value of beta, of that value of lambda. If you are close to that, anyway, the effect of resonance is felt. So the bar theory of meandering is not correct, but bars are related to meandering for this reason. I don't know whether I have been clear. I'm trying to summarize a very long work. So, okay, see, so this, you get something also that you find in any oscillator. Any linear oscillator has a change of phase when you cross resonance. And in fact, what you find here is that the meanders migrate downstream for relatively small value of the aspect ratio and migrate upstream for relatively large values of the aspect ratio. So when you cross the resonance, the phase changes, like in any linear oscillator. What happens after that? Well, let's go back to observation. What is the shape of meandering? This is something that geomorphologists have always been interested in. And a very famous geomorphologist called Luna Leopold, in 1964, told us that they are described by a curvature which is harmonic. It's not Cartesian. The curvature of the channel axis is a cosine of some lambda s. And this is how it fits, you see. This is the Mississippi River at Greenville, and that is the comparison between observation and this so-called sign-generated curve. 3 years before, a Japanese, which was completely unknown to the Western community, had done a similar and more interesting work, but he was not American, he was Japanese. And you know, he did this work using the photos of reconnaissance flight of the Second World War, because they didn't have Google at that time. So he used all these pictures, and he was able to show that the curvature in reality is a bit more complicated, in the sense that it has third harmonics, not second harmonics, but third harmonics. Why? The cosine describes fattening of the meander band, and the other term is a skewing coefficient. It describes skewing. Meanders may be upstream or downstream skewed. Some people claim they can tell you from the plane whether the water is going in one direction or the other, looking at meanders, because if they are skewed upstream, then you know where the water is going to. But actually, this is not true, because you can have both. Anyway, I showed you this because, you see, starting now from the non-integral differential equation, non-linear integral differential equation that I showed you before, you can get an exact solution. Exact solution. And this is not a classical, I would like to stress, this is not a classical Fourier expansion, because all these wave numbers depend on time. And they are connected to each other through this relationship, which depends only on one lambda of t, which describe the lengthening of meanders. But this equation, this solution solves exactly the nonlinear integral differential equations. And also, you see, if you truncate the expansion at the first term, you get exactly lambda in a Leopold. If you truncate it at the third, you get Kinoshita. So this expansion fits exactly what is observed, but it shows that the nonlinear integral differential equation shows exactly why you don't have second harmonic, because nonlinearity is cubic. That is the reason, because nonlinearity is cubic. As I said, there are no even harmonics. Okay. I think I have little time. Anyway, one more point for mathematicians. If you truncate the expansion at the first term, the interesting thing is that you get an amplitude equation for the fundamental, which is similar to Landau-Stewart, but it is not Landau-Stewart. It has some cubic term here, you see, that is not in Landau-Stewart amplitude equation. You can also show another important thing, that meanders of permanent form exist. There are no solitary wave, solitary meanders. And unless, let me be quick. You see, these look like a train of solitary meanders. But the reason why they exist is that there are valley walls which are inerodable. So this is a very interesting problem for mathematicians. I look at my friend Mario, solving the nonlinear integral differential equation inequality which describes the non-erodibility of the boundary. That would be, it can be solved numerically, but probably from the mathematical point of view could be interesting. Okay, and then, if you solve the problem, you get all the things that you have seen before. I don't want to bother you more on the fattening, skewing, and so on. Let me just close saying that the description that I told you stops when the two branches of the meander touch. When they touch, what is observed is a neck cutoff. So the meander is left completely. It forms a lake called Oxbow Lakes that you can see from the plane, and it starts again a cycle. Meanders are alive. They get dead and then they start again. Also, what happens after has been studied, but I will not bother you with any more details on this. This is a beautiful example of what happens. You see the Oxbow Lakes. This is the abandoned multiple loop, and you see the new meanders that forms, and they will start a new cycle. Okay, now I can stop here, or I can.
If you can talk about drops of COVID, you have 10 minutes.
No. I have a presentation, but in 10 minutes I would say nothing. And
Okay.
If anyone wants to see, there is a conference in the Accademia dei Lincei, and you just, if anyone is interested. But that conference is only about the fluid mechanics of the process. So how the process of drop formation, I would say, and dispersion can be described. And what problems are, let me tell you what I feel. From that point of view, the main point which has not been solved is not the fluid mechanics. Nowadays, the fluid mechanics of that process can be studied. Not so well the fragmentation, because people talk about droplets, but in reality, what you do when you cough or when you speak, you produce some filaments. And people have done very detailed experiments where you see that there are these filaments, or these called bags. And in a very short time, these filaments of bags break into small droplets. That process of fragmentation is a beautiful problem for those who do fluid mechanics. But it is very difficult and not solved. The other problem, how a mixture of drops let's say, in a humid environment, and depending on what happens in the room and so on, has been essentially solved. It's a classical computational fluid dynamics problem which has been solved also by people in my department. But the crucial problem which has not been solved is a biological problem. The biological problem is, okay, you are able to say if the bubbles, the drops that you produce evaporate or they do not evaporate, how long they move. They may even become dry drops, because the drops have a nucleus which is solid. The point is, will they be still infective? In order to decide how far from the person infection is transmitted, you must know that. And that is not known. And biologists have very strong difficulties in solving this, because it is difficult to make experiments on drops that move into the air to see if they are still biologically active. That is the major problem. So people who do fluid mechanics have enjoyed themselves, but I don't think in this case they are crucial. The crucial point is biology, in my view. Okay, there is a question, but my final I prepared this presentation thinking to have a young audience, but I see many white beards, so I apologize. No, it's just because my final message was, I cannot talk on this, of course. Okay, this is my final message. Thank you for your attention. Dove tutti camminano, difficilmente cresce l'erba. Grass hardly grows where everyone walks. Okay? Thank you for your attention.